Imagine a global blackout. No warning, just a sudden, total vacuum where the light used to be. This is Alex. He has a standard 800 milliamp hour emergency light. But in a world without a grid, that battery is a ticking clock. It's designed for a brief flicker of inconvenience, not the long-term survival stakes of a dead world. Within hours, he is left entirely in the dark. We have spent our lives psychologically tethered to the power grid. When it vanishes, we are left in a low-key lighting environment, a space of extreme contrast, where every step is dictated by deep, impenetrable shadows. The consumer tech has failed. To survive now, you have to stop looking for a working switch and start learning how to generate and manipulate light as a physical resource. In a permanent blackout, your most valuable tool is an understanding of the vacuum that remains. If you can't draw power from the wall, you have to harvest it from the physics of the environment. The sun rises, but the light stays outside. Alex's first task is survival through redirection, pulling ambient sunlight into the shadowed interior of his shelter. This is the angle of incidence. A beam of light striking a flat surface bounces off at the exact same angle. By aligning a reflective surface, Alex catches a single shaft of sunlight and throws it into a dark corner. He sets up a highly reflective metal plate directly opposite the window. It's a passive system that relies entirely on the math of the bounce. As the light reflects, it diffuses across the walls. This raises the overall visibility of the room without expending a single watt of stored energy. Mastering physics makes it possible to move existing light, rather than struggling to create new light from scratch. But the clock is always ticking. As the sun sets and the ambient light disappears, Alex is forced to actively generate photons to stay visible. He moves to a Tier 2 solution, building a fire. In a world without electricity, combustion becomes the primary practical light source. Fire is a chemical reaction, a process of rapid oxidation. As the wood burns, it releases energy trapped in the material for years, turning it into heat and light. This chart shows incandescence. The heat from the fire excites tiny soot particles until they vibrate fast enough to emit visible light waves. Alex amplifies this firelight using the same mirror from earlier. He places it behind the flames to bounce the light forward, effectively doubling the usable illumination in the room. By combining chemical generation with physical reflection, he has built a localized lighting system that functions entirely outside the grid. Alex eventually finds a high-capacity survival kit. This represents the peak of modern resilience. The system centers on a 12,000 milliamp hour lithium battery. Unlike the fire, which burns fuel immediately, this allows him to store energy for when he actually needs it. Using photovoltaic solar panels, Alex converts sunlight photons back into storable electricity. He is no longer just reflecting the sun, he is capturing it. This is a Fresnel optical lens. Instead of letting the light scatter like a fire, the grooved ridges in this lens catch the rays and align them into a single, concentrated parallel beam. This geometry focuses the LED's output into a penetrating spotlight, putting every lumen onto a specific target, without the wasted light bleed of a standard reflector. Resilience is the capacity to close the loop, to capture energy, store it in high-density cells, and use precise optics to apply it exactly where it is needed. Alex's survival depends on a three-part integration: the reflection of the sun, the combustion of the fire, and the solar conversion of the battery. Together, they keep the darkness at bay. The materials change, from metal plates to wood to lithium, but the underlying laws of physics remain constant. The grid acts as an automated shell for these rules, but the rules don't disappear when the power goes out. When the infrastructure fails, the physical laws of light remain. The only difference is who is doing the work to apply them. Mastering these principles is what keeps you out of the shadows. Subscribe to the channel to see how we apply physics to the world's toughest problems, and click the end screen now to see our next deep dive into survival science.